So yeah, let's just the two of us get started. It looks like it'll just be the two of us. So
Okay.
yeah. So yeah, I'm just beginning on the sentiment analysis section. So he sort of begins with the one of the famous data sets used in sentiment analysis, which is this IMDb movie reviews.
Mhm.
There is another one which is the Amazon product reviews, but IMDb is like the famous one as he sort of mentions here. And it's
Mhm.
quite nice because each of the reviews is just targeted as either being negative or positive.
Yeah.
Yeah. Some sentiment analysis ones they break it up into sort of more categories, but this is quite nice. It's just like two, positive and negative. Okay, the next bit. And then Keras has got built-in support for loading the IMDb data set
Yeah.
using this function. And it's interesting. Oops. Yeah. So what this actually gives you is a kind of interesting representation, which is it kind of creates a dictionary, and then sort of what you get back is actually the IDs of the words rather than the actual text of the words in here by default. So yeah, so he says, well, when you download this data set using this function, there's some pre-processing has been done on it. So all punctuation was removed. So exclamation marks, question marks, full stops, things like that, gotten rid of. And then all the words are converted to lowercase, and then finally split by spaces, and finally indexed by frequency. So low integers correspond to frequent words. Yeah, yeah, so these numbers, each word gets a unique number, but the value of it is basically the frequency. So the lower it is, the higher the frequency of occurrence of the word. And
So,
sorry,
so what does the one represent? So one represent it's the token for the word.
yeah, so basically, yeah, it's like the word ID. It's like just whatever the word this is. Obviously, this is the most common word in the vocabulary because it's at number one. Can't remember what is, probably A, because that's very common in
Ah,
sentences, isn't it? Um, so yeah, it's just a number that represents that word. Yeah.
okay.
And he says in this particular data set, the numbers 0, 1, and 2 are special um, because the 0 is used as a padding token, 1 is used as a start of sentence token, and then finally 2 is used for an unknown word. Yeah, so this, yeah, so yeah, so you have to be careful that you don't, that you're aware that the 0, 1, and 2 have this sort of special meaning. And he said, well, if you want to actually know what the words are, there's a way to decode these integer values back to the words that they represent. And there's a little bit of code here that does that. It basically gets this other data set, which is the get word index, rather than this load data. This is IMDb word index. And then he creates kind of like a dictionary which maps index values to words. And then he can use that dictionary to actually print out the actual words in a sentence based on the numbers they were given. So it's interesting that it might be that one is actually this um, in here, because if one, I don't know if he's used the same piece of data which is translated back into English, but it looks like in this case one might be this. Yeah. So I think um, so is that kind of okay so far?
Yeah.
Okay, so the next bit is, so in any real project, we will have to pre-process the text yourself. And that is like, instead of using this pre-trained data set, if you have to create your own data set, yeah, you have to kind of do some kind of pre-processing. And you can do this using the tokenizer class we used earlier. So I guess that was a little bit earlier on in this section. I must confess I missed the Sunday session, so I don't know if they covered the tokenizer. But anyway, it seems to be a class that you can give us a sentence to, and it'll actually create you these IDs, which are like the tokens.
Mhm.
And it's got some parameters on there. So it says, but this time setting char level equals false, which is the default. Um, okay, you can do that using the same tokenizer class we used earlier, but this time setting char level equals false, which is the default. Oh, okay. When encoding words, it filters out a lot of characters, including most punctuation, line breaks, and tabs, but you can change this by setting the filters argument. Most importantly, it uses spaces to identify word boundaries. This is okay for English and many other scripts, written languages. They use spaces between words, but not all scripts use spaces this way. Chinese does not use spaces between words. Vietnamese uses spaces even within words, and languages such as German often attach multiple words together without spaces. Even in English, spaces are not always the best way to tokenize text. Think of San Francisco or I love deep learning. Yeah, because really San Francisco is a single thing. Having that separated out into two, yeah, it just makes life a little bit more difficult. So yeah, I mean, obviously there's loads of different types of pre-processing you can do, but he's obviously mentioning, you know, some of the complexities of dealing with language, particularly if it's not English, if you're not, you know. So in some ways, English is quite nice in that it has these sort of really simple rule of spaces and punctuations, you know, which you can get rid of. Yep. And then he mentions some alternatives now. Instead of having to do all this kind of pre-processing, you know, to kind of make the vocabulary manageable, there's actually alternative ways of generating these tokens, which help with words that, you know, you've not come across in your data set, basically. So it says, fortunately, there are better options. The 2008 paper by Takukuda introduced an unsupervised learning technique to tokenize and detokenize text at the subword level in a language-independent way, treating spaces like other characters. Yeah, so this seems to be some kind of model which has been trained on how to split sentences. And then it can handle all different types of languages because it's trained on how the breaking up should happen. So, and it says, with this approach, even if your model encounters a word it has never seen before, it can still reasonably guess what it means. For example, it may never have seen the word smartest during training, but perhaps it learned the word smart, and it also learned that the suffix est meant the most, so it can infer the meaning of smartest. And then we've got a couple of algorithms. So Google's Sentence Piece project provides an open source implementation described in a paper by Takukuda and John Richardson. So yeah, there's this one implementation of this approach. And then another option was proposed in an earlier paper by Rico Senrich that explored other ways of creating subword encodings, for example, using byte pair encoding. Last but not least, the TensorFlow team released the TF text library in June 2019, which implements various tokenization strategies, including WordPiece, a variant of byte pair encoding. This whole approach to kind of tokenizing, it kind of comes through into BERT and the more modern systems as well, because everything needs a tokenizer. It needs a way of converting the text into some kind of a numerical representation, which you can use. So yeah, these are a couple. I think BERT uses byte pair encoding in the tokenizer. Yeah. Is that kind of all okay so far?
What's the byte pair encoding?
Yes, so essentially what that involves is splitting the word into different sizes of subwords, and it depends on how many, you know, how many subwords, you know, how many subcharacters that you're using. So it is, I mean, that's a very simplified explanation of it. So let's see if the byte pair encoding. I wonder if there's a reasonably good description of it. So what is byte pair? So let's have a look at. Okay. So okay, right. Okay. So. Okay. So this is strange. Okay, yeah, I'm not quite sure how they use it to actually break up into tokens then, because in this example, it's saying, well, the way byte pair encoding works is that you take the most common pair of characters, replace them with a new character, which is not used previously. Then you look at the most common occurrence again, and then split that up into another character, and then replace that, and then you carry on doing that, basically. And then so the final representation is actually this guy. It's sort of like it's almost like a compression type algorithm here.
Yeah.
Yeah. Okay. As I must confess, I didn't fully understand how Viper encoding works. I might sort of look into it and see why they do this, because what we're really interested in is splitting the words into tokens. So I don't know how this helps into splitting them into tokens. Okay, I'll look into it. Okay, and then so that's that bit. And then it says, if you want to deploy your model to a mobile device or web browser and you don't want to have to write a different pre-processing function every time, then you will want to handle pre-processing only TensorFlow operations and can be included in the model itself. Let's see how. First, let's load the original IMDb reviews as text using TensorFlow's datasets introduced in chapter 13. Yeah, so this basically sort of saying that some TensorFlow kind of modules do a lot of this for you, so you don't have to manually do that, but you have to, you have to use the correct model, I guess. So here he's loading the IMDb reviews. So he's setting as supervised true and with info true. And then he's got, okay, so example. Now let's write the pre-processing function. So this is kind of raw data, almost. And this pre-processing function, first of all, fetches 300, or chops it off at 300 characters. And then replaces this BR slash, this is HTML for line break, with a space. And then anything that's not A to Z or A to Z or a single quote replaces with a space. Yeah, okay, so this is, yeah, he's got slightly digressed here, because this is basically a preprocessor you could use. And what that's doing is, if you've got a string like this, well, I can't, and then with a BR slash, which is HTML for line break, basically it's going to split off the comma and convert it to a space there, and actually delete that bit altogether. So that all you got is, well, I can't, because it'll only accept characters that are letters and single quotes. And everything else is either converted, replaced altogether, or replaced with spaces. So yeah, it's just one example of a preprocessor that you could write. But obviously there's others. So yeah, it's strange why he was kind of mentioning here about how it could be already be done by the TensorFlow code, and then he's actually written one. Is that okay? Yeah, he's just written a preprocessor.
Yeah.
Okay, cool. And then he's saying something about and then padding. So padding is used quite a bit, because the all the reviews are like all different shapes, all different sizes, and obviously machine learning algorithms, particularly keras and deep learning, they like all the vectors to be the same size. So you need to do something to the smaller bits of data. So they've got this special token called pad, and it was one of those three that he mentioned, the special ones that are added manually to the dictionary, and pad's one of those. So does that make sense how they use pad?
Yeah.
Yep, cool. Okay, and then we move on. Okay, so this is a little bit of a walkthrough of how they generate those integers that those numbers we saw, these numbers here. So there's a little bit of a walkthrough on how they sort of take the the raw data and actually generate those numbers in terms of like code. I don't know if it's worth going through those.
Yeah. So one question is like, so what he was saying is the most frequent word will be listed in the beginning and
yes.
in a descending order, but that has nothing to do with the ID which it get assigned to.
It will, because the index in that table is what the ID is. So like the most
smaller ID. Yeah, in a sense, the frequency is only, we wouldn't know how much is the frequency is, except the positioning. It's just the positioning of the word.
Yes, you're quite right. All we'll know is,
and why do they keep that in descending order?
Okay, so I think this is to kind of manage the size of the vocabulary. So basically what he's, yeah, and I'm not sure I totally agree with it, but basically what he's saying is, obviously English has got probably over 1 million words, yeah?
Yeah.
But we don't want to have to deal with the vocabulary the size of 1 million. But it's highly likely that if we only count, say, the top 50,000 words, that actually all the data we need to classify sentiment is in those 50,000 words. And the other words that occur, we just don't care about them. Yeah.
Okay.
We just pretend they're all like one word, which is unknown word, which is one of the special words that they've got in the dictionary. You know, those first three, there was a padding one, there's an unknown one. Yeah. So I think this is just to manage the size is why we would use the most common ones. Although in theory, the ones that are least common are interesting in some way as well, because they maybe say something really special about that sentence. But yeah. Yeah, sorry, I stopped you from talking.
No, it's all right. Yeah, I understand what you said there.
Yeah. Yeah, so this is a little bit of, so the final output is the numbers that you know that you originally did. So yeah, it's all about kind of building a dictionary, using the most common words, truncating it to that much, and then whenever you're given a bit of text, looking it up in that text. And if it doesn't exist, obviously you'll have to manually set it to that unknown y. Yeah, so here we go. So while the word fantastic was not found, it was mapped to one of the outer word buckets with an ID greater than or equal to 10,000. So in this case, he's, yeah, I mean, this algorithm is not doing exactly what the other one did, so it's a little bit confusing. And then we've got the encoding. Okay, so here now is finally a model that he's going to use to actually do the sentiment classification. So yeah, this is the sort of model you would need. So this is a sequential model. The very first layer is an embedding layer. And then after that, we have a GRU layer, and a dense layer. So have you come across these embedding layers, what these guys are?
Yeah.
Okay, so they just map, yeah. So they map one of those IDs to actually a vector of size 128 in this case.
Yeah.
So that the words get so instead of using the original integers that we had, we actually use a vector of dimension 128 for each of the words, and this embedding is actually learned. So it's like a this guy is quite sophisticated in that it's in your code. Yeah, the values for the embeddings will actually be learned instead of just being hardwired.
Mm-hmm.
And then GRU and LST is a type of recurrent layer. So we covered RNN before Christmas, and GRU is a type of RNN. It's and LSTM is the other one. So have you ever heard of GRU?
Yes, I did.
Yeah, cool. Yeah, so in this case, what he's done is the embedding is the very first layer. That feeds into a GRU layer, which outputs 128 dimensions, feeds into another GRU layer, which outputs 128 dimensions. And then finally, that it gets all compressed into a single value, which is returned using a sigmoid. And we use the binary cross entropy loss, because all we're looking for is between 0 and 1. 0 is one sentiment, 1 is the other, to compute the loss function. And then, yeah, so that's the kind of like the complete model that he's got here. Is that all okay?
Yeah.
Yep, cool. Yeah, so he's got a little bit of a description about this model. Sorry.
One question I have. You see the loss is binary cross entropy. Yep. Sometimes they use a sparse binary cross entropy. And I think we covered somewhere. Would you know the difference between the two?
I'm not sure about sparse binary. I know they do sparse cross entropy because that's in the next section. So look, give me 1 second. What's the next one? It's so that's binary cross entropy. Yeah, that's interesting. Yeah, so that's binary cross entropy. That's 128. Dense layers. That's sigmoid. So, yes. Sorry, give me 1 second. Dinesh, because like encoder, decoder, Okay, so this guy, where was the loss function here? So softmax, there's a whole lot of layers. And then, yeah, okay, so where was it? So look, so you're saying sparse binary cross entropy.
No, I think maybe I'm wrong. So it may be that sparse cross entropy there.
Yeah, sparse cross entropy makes sense. Not sure. I mean, who knows? I mean, people play with also dealing with sparse categories in binary cross entropy loss. Okay. Okay. And so what is this? So there's a binary cross entropy there. Sigmoid cross entropy logits. Yeah, I think the one you're talking about is the sparse cross entropy.
I think.
And and there's also this sampled version of it as well, where yeah, we're just going to come to that in a second, actually.
Okay.
Yeah. So there's a little bit of a description about this model, and then he's talking about, okay, what do we do about all the, because a lot of this data is not the same size. Some reviews are short, some reviews are bigger. And we had those kind of padding tokens, but actually what we would quite like to do is completely ignore them altogether. We don't want all that kind of adding to the computation, because really that's that's not even data the model should be even be looking at, because that's just our way of kind of making it fit. And so there's this notion of masking, and so Keras' layers, the GRUs and the RNNs actually handle masking as a special operation. And essentially what you do is wherever there was a padding character, you actually set the mask as 1, and wherever it wasn't, you set it to 0. And then the RNN layers know that when they come to a masking layer, they can stop operating. Or as soon as they come across a masking token, they don't have to go any further, because this is the end of like the input they need to process. So like if, let's say, you had like a the input size was 256 kind of words, normally an RNN would go through each single one and then output the final hidden state at the end. But with kind of masking, there's like an early stopping. If the sentence only created had 50 words in it, it would only operate the RNN for 50 time steps and then stop and give the hidden state, because the masking is stopping the RNN from doing any more work. Does that make sense?
Yeah.
Yeah. And he's saying, well, all this is kind of hardwired into the coding of certain of this embedding layer and the GRUs and the RNN layers. But he's saying the LSTM and GRU layers have an optimized implementation for GPUs based on NVIDIA CUDNN library. However, this implementation does not support masking. If your master model uses a mask, then these layers will fall back to the much slower default implementation. Yes, it's going to use the CPU. Yeah, so masking is great, but unfortunately, at least with the particular version when this book was written, these two systems didn't implement the masking properly in the GPU. I guess which sort of makes sense, because GPUs really like matrix multiplications. They don't like loops and things like that. So it's probably quite tricky to implement this kind of algorithm of masking in a GPU. Yeah. Well, that's my pet theory. That's just based on kind of ill-informed opinion. Okay. Right. So let's carry on. And yes, mentioning a couple of other layers that actually also implement masking, and then says using masking layers and automatic mask propagation works best for simple sequential models. It will not always work for more complex models, such as when you need to mix a convolutional 1D layers with recurrent layers. In such cases, you will need to explicitly compute the mask and pass it to the appropriate layers using either the functional API or the subclassing API. Yeah, so if you use a mixture of different layers, then you will have to propagate the mask yourself, because the layers won't do it for you automatically. Okie dokie. And then let's look. And then he sort of goes through and kind of implements. So what is this, guys? So we've got an embedding layer, GRU layer, dense layer. Oh yes, yeah, it's the kind of pretty much what we were looking at before. And yeah, it says, and so basically training this for a few epochs on that IMDb data, this model will become quite good at judging whether a review is positive or not. If you use the TensorBoard callback, you can visualize the embeddings in TensorBoard as they're being learned. It is fascinating to see words like awesome and amazing gradually cluster on one side of the embedding space, while words like awful and terrible cluster on the other side. Some words are not as positive as you might expect, at least with this model, such as the word good, presumably because many negative reviews contain the phrase not good. It's impressive that the model is able to learn useful word embeddings based on just 25,000 movie reviews. Basically, that's the data set, 25,000 training set. So yeah, so it's interesting. It's saying, that even with just this amount of data, you're actually going to get reasonable performance. And the word embeddings that you come out of it are actually, interesting, as it were. Does that is that all okay?
Yeah, that's all fine.
Yeah. Yeah, it says, and imagine how good the embeddings would be if we had billions of reviews to train on. Unfortunately, we don't, but perhaps we can reuse word embeddings trained on some other larger text corpus, for example, Wikipedia articles, even if it is not composed of movie reviews. So this is sort of like what BERT will be eventually doing on that huge, massive data set that it's been done. Obviously, the model is a little bit different, but yeah, it's all, the whole notion is that we want to get some really good embeddings from, which we can use, for all sorts of other purposes.
Mm-hmm.
Okay. And then it says reusing pre-trained embeddings. Yeah, so transfer learning and reusing models is like huge now, because the cost of training a lot of these models is so enormous. So the TensorFlow Hub project makes it easy to reuse pre-trained model components in your own models. These model components are called modules. Simply browse the TF Hub repository, find the one you need, and copy the code examples into your project. And the module will be automatically downloaded along with its pre-trained weights and included in your model easy. Yeah, so it seems like, so this module concept is quite interesting, because apparently it's able to do the pre-processing for you as well. So you not only get all these pre-trained weights and a model, but you get some utilities already applied in the pipeline to help you out. So here we have, so for example, let's use the NNLM English Dimension 50 sentence embedding module, version 1 in our sentiment analysis module. So we've got hub. So this is sequential layer. So the first layer is this Keras layer, which is being downloaded from the internet. Then we have a dense layer, 128, and finally a dense layer of sigmoid. And then it uses, okay, sorry.
So this is the module is nothing but like the glove embedding we download, or we go for some other. I think there is another kind of embedding we have. We just download and then use it in our model. Is that what the module he means?
Yeah, so I mean, so this is, I mean, I haven't used this, but he's saying here, he says the hub Keras layer downloads the module from the given URL. This particular module is a sentence encoder. It takes strings as input and encodes each one as a single vector, in this case, a 50-dimensional vector. In turn, it parses the string, splits words on spaces, and embeds each word using an embedding matrix that was pre-trained on a huge corpus, the Google News 7 billion corpus. Yeah, so it seems like this Keras layer is not just like pre-trained word embeddings, which it is, because it outputs 50-dimensional vector, but it's also got some kind of utility. So I'm not sure. So I don't know if he hasn't given an example of what you feed as input to this thing. I'm guessing it's just a single sentence. Sentences are what get fed into this thing. But it's almost like this guy. It's like a combination of utility functions to parse the input and kind of pre-process it, and as well as a whole load of learned embeddings as well, which can be preloaded into the model to use it with. So yeah, it's kind of like an amazing kind of, also, functionality that, in just a couple of lines, you get like a huge amount in there. I don't know if that makes sense to you.
Makes sense, yeah.
Yeah, I might have to. I don't know. I'm not really into keras, but like this is such a small amount of code. I wonder if in the he uses it in the next. Okay, so yes, yeah, he has got a small warning about this keras layer that by default, this keras layer is not trainable. But you can set trainable equals true when creating it to change that, so you can fine tune it for your test. So it's just a little warning on how to do it. So what's he doing? Next, we just can just load the IMDb reviews dataset. No need to pre-process it except for batching and prefetching, and directly train the model. So this is where loading it without any pre-processing. We split it with a batch size, and then we. Okay, yeah. So yeah, it just takes as input the sentences, individual sentences. Interesting. Or individual reviews, should I say, and it'll do the padding and the truncating or whatever else it's doing internally. I guess it'll have extra parameters to see what the size of the individual sentences it should handle is and stuff like that. Okay, and then he mentions a little bit about the fact that that layer is actually doing quite a lot because it's downloading stuff from the internet. By default, it puts it into a temp folder, but you can actually set an environment variable, which is the TF hub cacher, so that basically you don't want to have to, you don't want to have to each time you run it download download the model and download all the data. You'd rather have it cached, which is what this will do. So first time you run it, it will download it and cache it in this folder, and then next time, obviously, you do it, it'll check if it's already there and just you use it from there, which is quite nice. Because some of these models are really huge, well, I mean, this one, I don't know how big that is, but the BERT ones sometimes are almost a gigabyte in size. Okay. So is that kind of okay?
Yeah, that's fine. Yeah.
Yeah. We'll just, don't know if it's worth doing this encoder decoder. Okay, we'll just do it quickly because the guys on Sunday might do it again, because obviously this was all really quite dense. And I doubt they'll get to this bit, but I guess if we do it quickly, and then on Sunday we could just get a recap of it with those guys.
Yeah. Sounds good to me.
Yep. So encoder decoder is for machine translation. So this is, for instance, taking translating English to French or French to English or German. So okay. So and this is using what's called an encoder decoder architecture. So yeah, so the idea is that so this is the encoder. You're feeding the English sentence into it, and the RNN is kind of operating and then outputting a state, and then the decoder is being used to use that state, and then that is kind of iterating to generate the actual final translated output. There was an interesting little note that English sentences are reversed before they are fed to the encoder. For example, I drink milk is reversed to milk drink I. And this ensures that the beginning of the English sentence will be fed last to the encoder, which is useful because that's generally the first thing that the decoder needs to translate. It's an interesting, yeah, I hadn't thought that this would be useful, but yeah, I guess it makes sense that the model should really focus a lot on I drink first. Because the hidden state, this bit of it should be like the topmost bit of it in the hidden state. And then when the decoder starts, this is what it's kind of starting with, knowing, although,
so
yeah.
How does it means that if we reverse it, so let's say if we say I drink milk,
Yeah,
and then it's going in a parallel, does it mean like it going parallel? So we are having a encoding, and then it going to be having a embeddings, and then those embeddings going encoder. So on the top, it's the like when we look at the yellow boxes, so that's like it's reading from right to left as a I drink milk. Is that what it means?
okay, so this is a little bit confusing because it looks like things are being fed in parallel into it, but they're not really. They're fed one at a time. So one word at a time is going to be fed into this guy, yeah, per sentence. We'll ignore batching for the minute because that slightly complicates things, but let's assume there was a batch size of 1. So one review at a time or one sentence at a time was going to be fed into this thing, yeah? And the way you would feed it in would be one word at a time. So first of all, because it's reversed, you would first feed it in the milk word, and that would then get operated and generate some state.
Yeah.
And then you would feed it the drink word, and that would take the input that was generated the previous in the previous step, as well as the new word, and generate another output.
Yeah.
And then finally, you would give it the I word, and then that would take the output of what the previous state was, as well as the I, and kind of compute something, and then give a final output. And then it's that final output that's going to go into the decoder.
Yeah.
So this is done one at a time, one word fed at a time.
Okay, so why did they do the reverse then in that case?
So basically, I mean, as I say, I don't really fully agree with it, but he's saying that that the decoder, the first word that it's really interested in is I. Yeah. Somehow it's needing to think about what should I do with I, shouldn't it? Yeah. Because I mean it depends on the language. I mean, I can't imagine there's a weird language where everything is back to front. But if I'm translating English to French, and the word my sentence begins with I, then the decoder should really be quite interested in how to translate I. Does that make sense? And he's saying, well, it's
my point is when the encoder passed the hidden state to the decoder, it's going to be just a one updated value. It's not the decode of I separate to the decoding of a drink to the decoding of a milk. What has been passed to the decoder, it's going to be the final hidden state.
I totally agree. Yeah, I mean, this is why as I said, I'm not 100% convinced you really need to do this reversing, but I just wonder if reversing it just helps to create a slightly nicer hidden state, which the decoder finds a bit more useful. I mean, you don't, strictly speaking, need to do it, as you say, because it's still one final state that you go to the decoder. You're not giving it bit by bit. The encoder has created some high dimensional kind of vector, and that whole vector is what you're feeding into the decoder once it starts decoding. But I just wonder if they've experimentally discovered that giving it the reverse improves the performance of the decoder on a certain size of hidden state. That having this bit processed last by the encoder helps this guy to get started. But as you say, I can't see exactly what the reason would be, because the whole thing is still one hidden state. Yeah, I agree with you. Yeah.
Okay. We will take it what he says.
Yeah, let's see what they say at the weekend. Because as you say, I mean, if the two were running in parallel, like when I fed it I in here, and then somehow that fed into the decoder, and the whole thing was operating like in some kind of sequential, somehow synchronized way, then I can imagine a situation where that would matter which order you gave it things in. But this is all operating in isolation. It's all kind of creating this state, and then this guy is operating independently afterwards. So yeah, I don't know. Okay, so and then says at each step the decoder outputs a score for each word in the output vocabulary, i.e. French. Yeah, so if the vocabulary of the output is 50,000 words, like those are the French words that we're interested in, this is going to give a score for each individual word. And then the softmax layer turns these scores into probabilities. So is that kind of okay? Because this is just, the one hot kind of type. Well, basically, this little bit of his, all it's going to tell us is what's the highest probability word at this point. Yep.
Yeah.
And then it says, for example, at the first step, the word je may have a probability of 20%, tu may have a probability of 1%, and so on. Yeah, so it's just saying, so probably the word we should be choosing is je. Oops, let me, never mind. Let's have a look. Okay, then it says, okay. The word with the highest probabilities output, this is very much like a regular classification task. So you can train the model using sparse categorical cross entropy. Yeah, so this is the bit that we were talking about last, much like we did in the char RNN model. Note that at inference time after training, you will not have the target sentence to feed to the decoder. Instead, simply feed the decoder the word that it output at the previous step. Yeah, so I mean, when during training, obviously we know what the French output should be. While training, the input, the very first input to it is kind of start of sentence. But then we actually feed it what we expect it to give and then work out what it did give. And then that's the kind of the loss function is applied kind of in that way. But when you're actually using it in practice, obviously you're not going to have the translations. So they're saying at each step, just give it as input what the previous output was to kind of keep it ticking along. So that's how you use it in practice when you actually want to use it at inference time rather than at training time. Does that make sense?
Not really. So can you repeat what does it mean by giving a one step before?
Okay, so I mean, this is a little bit confusing because it looks like all these things are happening in parallel, but they're not, yeah? So at the very first step, what we're going to do is say during training, we've got a start of sentence token. You know, let's say this, you know, whatever the sentence this was, which is I drink milk, is je bois du lait is is the sentence. So during training, we know what the actual output should be.
Yeah.
So during training, the first input to the RNN, this decoder would be the start of sentence token.
Okay.
And then we would compare it to J because that's what we were expecting it to have. So the loss function is, so the target was J, and whatever its prediction is giving, that's where the loss will happen. Yeah. And then at the next time step, we know it should be, say, Bui, you know, this is 2 steps down the road now. And so we feed it, you know, Bui, and then we're expecting it to give do, are we? Yeah. In this case, it's actually outputted lay, but do. So each one of these is one individual step, yeah, which is what we're doing to it is we're giving it what it should have output, and then comparing it to what it did give as output and comparing it to that target, yeah. So that's where the loss is kind of, that's how we're going to train the decoder, is telling it what it should have done, and then checking that it's actually doing it, yeah.
Okay.
Okay, so this is during training time where we knew exactly what the sentence was going to be that it should be outputting, yeah?
Yeah.
But, okay, but now we're going to, let's say that we've got another sentence that we've actually encoded now, and the final encoding, you know, the final hidden state is here. How do we now get it to actually generate the translation? So the very first input we give it to it is the start of sentence, yeah? And it will output some word that it thinks is what is how the translation begins, yeah. This is at actual inference time, so this is when we're actually using it. Yeah, it's not training now, this is actual using it. And then what we do is at the next step, we actually give whatever it output as the next input to it, and the hidden state that you know, the next hidden state, because the hidden state is being kind of mutated while it goes along. And then it's using what it actually gave what it output gave as input, and then generating the next word after that. And then we're doing exactly the same thing. We're kind of feeding it what it gave as the previous word, because when it was trained, it was always trained on some sort of hidden state and the word, current word that it's on to generate the next word. And then and that was at training time. But at and then when we're using it, we have to kind of feed it what it generated to kind of keep it ticking along, using the hidden state to kind of say how I would unroll the whole sentence out. Yeah. Okay. Okay. Yeah. So this is kind of like, this is a little diagram of like feeding. So the very first at inference time, we give a start of sentence and the hidden state. At the next step, we give it the output of the previous hidden state as well as the output from the last sentence. And this generates another word, and then we feed that word and the output of the hidden state, and we kind of keep ticking around like that. And each of these is one step at a time. It's not happening in parallel. Yeah.
Yeah.
Okay. Cool. And then he's got a little bit about. So far, we assume that all input sequences to the encoder and the decoder have a constant length, but obviously sentence lengths vary. Since regular tenses are fixed shapes, they can only contain sentences of the same length. You can use masking to handle this, as discussed earlier. However, if the sentences have very different lengths, you can't just crop them like we did for sentiment analysis, because we want full translations, not cropped translations. Instead, group sentences into buckets of similar lengths. For example, a bucket for the 1 to 6 word sentences, another for the 7 to 12 word sentences, so on, using padding for the shorter sequences to ensure all sentences in a bucket have the same length. Check out the TF data experimental bucket sequence function for this. For example, I drink milk becomes pad, milk drink I. Did that kind of make any sense as to why they're doing this?
No.
Okay, so what they're saying is, let's say that you're translating, yeah? Well, you got sentences of all different sizes that you could be training on, yeah?
Correct.
So some of 2-3 words, some 20 words, some 30 words. And what they're saying is, and as I said, I'm not quite sure what their reasoning is internally, but what they're saying is, ideally, what you want to be doing is training sentences that are roughly the same length, in that because we're using this masking, that we don't want to have like one sentence which has only got 2 words in it and everything else is masked, and another sentence which has got full 20 words in it, and we're training those two kind of like in the same batch, because that's going to cause the the weights to to be adjusted in some weird way, because one of those sentences contains quite a lot of information and the other one hardly contains any information. So what they're saying is, instead, kind of break your data sets up into similar sized sentences, so that it's similar amount of information going into the network at each training step. And you're going to get, their reasoning is that you'll get better performance that way, instead of having this really lopsided one where you've got like one sentence with 20 words and one sentence with only 1 word in it, and you're trying to train the network on both of those in parallel. That's just not going to work very well. Okay. I could sort of understand that. Yeah.
Yeah, makes sense. Yeah.
And then they say we want to ignore any output past the EOS token. So these tokens should not contribute to the loss. They must be masked out. So, okay. So basically, because we're using fixed lengths of sentences during training, let's say all our sentences are 20 words long. And then so some sentences might be 15 words, some 13, some 20. And what they're saying is that basically, as soon as you come across an end of sentence token in the output, you want to stop doing any kind of loss computations after that, because all the stuff after that is kind of gibberish, because in real life, you won't even look beyond there, because the idea is that as soon as this network outputs EOS, that's it. That's the end of the translation. If you keep because it's just an RNN, you can keep feeding it and it'll go on forever doing something. But after that, it's highly likely to be gibberish. So you don't want to train on that aspect of it. So yeah, so stop computing the loss after you've come across an end of sentence, basically, token in the output. Does that make sense?
Yeah.
And then they say, when the output vocabulary is large, which is the case here, outputting a probability for each and every possible word would be terribly slow. If the target vocabulary contains, say, 50,000 French words, then the decoder would output 50,000 dimensional vectors. And then computing the softmax function over such a large vector would be very computationally intensive. Yeah, so you'd have to, that's a huge softmax computation. To avoid this, one solution is to look only at the logits output by the model for the correct word and for a random sample of incorrect words, and then compute an approximation of the loss based on only these logits. Did that make any sense, or is that like confusing what they've done there?
It's confusing, totally confusing.
Okay, so what they're saying is the network itself has computed you 50,000 outputs, yeah? Because that's your vocabulary size. You don't want to go and compute 50,000 softmax, because that's like a huge calculation, yeah? So you know during training what the correct value should be, yeah? So let's take the network output for that one, so this logic for that one, and some other incorrect ones which are random, selected. Let's say you select 20 other random ones. You choose one correct one, so the value for that, and 20 other ones which are incorrect, and only compare those. Only compute the softmax for those. So you're not computing a 50,000 softmax. You're only computing a 21 softmax, the correct one, and 20 others to kind of, and this is called sampled softmax, and this is one way of kind of training it. I mean, in theory, so long as you use a reasonable size for the random incorrect ones, it should still give you pretty good performance. You shouldn't have to compute, the full softmax on every single one of them to do it. Yeah. So that's basically. They're saying obviously sample softmax cannot be used at inference time because it requires knowing the target. So when so during training you can use this guy, but actually when you're finally using it, you will have to compute the full softmax to work out which word it is that it's trying to output to you. So yeah, which makes sense.
Yeah, makes sense.
And then they've got an implementation of this encoder decoder architecture using an LSTM. And then they've got this notion of a bidirectional RNN, which is basically two stacked, one going in one direction, one going in the other direction. And there's actually a layer called bidirectional, which does all that for you, thankfully. So you just tell it that it's a GRU of dimension 10, and I want a bidirectional one, and it'll do the both direction for you, which is quite nice. And I think that's about it. And then they go to beam search, which is kind of a slightly different thing. But hopefully the guys will cover this aspect of it again at the weekend. And yeah, we can have a chat.
I'm not sure what they covered until yesterday. I'll ask them what they covered.
Yeah. I don't know. I don't think I saw anything in the.
No, I'm gonna ask for recording. So probably they haven't put anything.
Yeah. Interesting. Yeah. Okay. So yeah, we'll hopefully catch up at the weekend.
Absolutely fantastic. So you're joining us on Sunday, yeah?
Yeah, I should be. So cool. And yeah, have a nice week, and I'll speak to you then.
Your time, and then you too have a nice weekend.
Yeah, you too. All right. Bye.